In the summer of 1918, a scientific paper was read aloud to a Royal Academy in Germany by a man who did not write it, because the woman who wrote it was not allowed in the room. It was 23 pages long. Einstein called its author a genius. A century later, physicists rank those pages alongside anything he ever produced. And yet most people have never heard her name. Her theorem answers a question a child could ask, and 200 years of science could not. Why can energy never be created or destroyed? The answer was hiding inside every spinning skater, every orbiting planet, and every wire in your house. And it is stranger and more beautiful than the rule it explains. By the end of tonight, you will know exactly what Emmy Noether saw, and once you learn it, you will not see the world the same way. Before we begin, if slow journeys through big ideas are how you like to drift off, a quick like or subscribe truly helps the channel grow. It costs you a moment, and it means a great deal to me. Now, let's begin. The most important letter in the history of physical law was addressed to a woman who was not allowed to hold a job. It went out from Göttingen, Germany, in the spring of 1915, and it travelled about 300 kilometers south to the quiet Bavarian university town of Erlangen. The two men who sent it were, by common agreement, the most powerful mathematicians alive, and the woman who opened it was working, at that moment, for no pay, with no title, in a building where she had once been forbidden to enroll as a student. Her name was Emmy Noether. Within 3 years of opening that letter, she would prove a result so far-reaching that a century later, physicists routinely rank it alongside anything Einstein ever produced. It is not a theory. Theories can be wrong, and the history of physics is a graveyard of beautiful theories that were. It is a theorem, a piece of mathematics, proven once and true forever. And what it proved would quietly change what the laws of nature actually are. Not what they say, what they are. We will get there. But to understand why that letter was sent, you have to understand what was happening in Göttingen in 1915, because the letter was not an act of generosity, it was an act of something closer to desperation. Göttingen, in those years, was the center of the mathematical world. It is difficult to overstate this. Carl Friedrich Gauss had worked there. Bernhard Riemann, whose curved geometry would one day carry Einstein's gravity, had worked there. By the early 20th century, the tradition had passed to two living men. Felix Klein, the great organizer, had spent decades building Göttingen into an empire of mathematics, gathering talent the way other empires gather territory. And David Hilbert, widely regarded as the greatest mathematician of the age, had in 1900 stood before the International Congress of Mathematicians and listed 23 problems that would set the agenda for the next century. Mathematicians had a saying, only half a joke, that there was no life outside Göttingen. If a difficult idea existed anywhere in the world, sooner or later it walked through that town. In the summer of 1915, the most difficult idea in the world did exactly that. Albert Einstein arrived from Berlin at the end of June and gave 6 lectures on his general theory of relativity, his still unfinished attempt to explain gravity not as a force reaching across space, but as the shape of space and time themselves. The theory was incomplete, its final equations still months away, but the audacity of it was fully formed. Einstein was proposing to replace Newton's universe, which had stood for 228 years, with something stranger and more beautiful. The Göttingen mathematicians understood him immediately, perhaps better than anyone else on Earth. Einstein wrote afterward, with real happiness, that everything in his theory had been understood down to the details. Hilbert, for his part, was so taken with the problem that he began racing toward the final equations himself. That November, in one of the most examined months in the history of science, Einstein completed the theory in Berlin, and the general theory of relativity, the theory that still stands today as our best description of gravity, the theory your phone's navigation quietly corrects for every single day, was finished. And almost immediately, the mathematicians of Göttingen noticed that something inside it was broken, or if not broken, then deeply, disturbingly strange. The trouble concerned the one principle that physics trusted above every other, the conservation of energy, the rule that energy can be neither created nor destroyed, only transformed, the rule that had been tested in steam engines and waterfalls, in chemistry and in starlight, for 2 centuries, and had never once failed. Every physical theory anyone had ever written down respected it, and more than respected it. In every earlier theory, you could point to the energy, add it up, and prove that the total never changed. Energy conservation was not a decoration. It was the load-bearing wall of physics. Engineers designed with it. Astronomers calculated with it. Every laboratory on Earth assumed it before breakfast. But when Klein and Hilbert went looking for that wall, inside Einstein's new theory, their hands closed on fog. Each time they tried to write down the total energy of a gravitating system and prove it was conserved, the mathematics produced something hollow. The expressions they derived were either true in an empty way, the way the statement 0 equals 0 is true, correct but containing nothing, or they changed their value depending on the coordinates chosen to describe them, which is something no physical fact is ever permitted to do. The distance between 2 cities does not depend on whether your map is printed in miles or kilometers. The energy in a room should not depend on how you label the points of space. Yet in general relativity, every candidate for the energy of the gravitational field behaved exactly that badly. Written one way, a patch of empty space seemed to hold energy. Written another way, the same patch held none. The number moved when you changed the map. Hilbert, who did not frighten easily, found himself asserting something remarkable. He claimed that in Einstein's theory, the usual energy theorems did not exist at all, that the theory possessed only what he called improper energy theorems, shadows of the real thing. And he suspected something more remarkable still, that this was not a flaw to be patched, not an error in anyone's algebra, but a structural feature of the theory itself, that any theory built the way general relativity was built would have to behave this way. It was a suspicion he could not prove. Klein and Hilbert circled the problem in letters and conversations, 2 of the finest minds of the century, and the problem did not move. Consider what was actually at stake in that impasse, because it is easy to miss at a century's distance. The most successful new theory in the history of gravity, a theory that was already explaining a wobble in the orbit of Mercury that had defied astronomers for 60 years, appeared to misplace the most trusted law in all of science. One of 2 things had to be true. Either the greatest theory of the age was wrong, or physics's most sacred law was not what everyone believed it to be. Neither option was thinkable. Both could not be avoided. So Hilbert and Klein did what Göttingen always did when confronted with a problem beyond its powers. They went looking for the one person in the world whose powers fit the problem. The mathematics at the heart of the difficulty was the mathematics of invariance, the study of expressions that hold their form while everything around them is transformed, stretched, relabeled, and rearranged. It is a strange and demanding specialty, and the deepest living master of it was not a professor in Berlin or Paris. She was an unpaid lecturer in Erlangen, standing in occasionally for her ailing father, publishing quietly brilliant work from the margins of a profession that refused to admit her. There is a detail here that history seems to have arranged on purpose. 43 years earlier, in 1872, Felix Klein, the same Felix Klein, had launched his career in that same small town of Erlangen, with a manifesto now known as the Erlangen Program. Its central idea, that a geometry is not really a collection of shapes, but the study of what stays the same while everything else changes. That idea had been planted in Erlangen 10 years before Emmy Noether was born there. She grew up, in the most literal sense, in the town where the question had been asked. And now Klein himself was writing to bring her to Göttingen, because Einstein's gravity had turned that abstract question into the sharpest crisis in physics. When everything about space and time becomes flexible, what, if anything, holds still? She said yes. She packed her things and moved to Göttingen, into the middle of the crisis, into a university that would spend the next 4 years refusing to give her a title, a salary, or a classroom of her own. What she did with that crisis is the subject of tonight's journey. But before we can watch her solve it, we need to understand who she was. Because the road that brought Emmy Noether to that letter is itself one of the strangest and most quietly heroic stories in the history of science. The world's greatest mathematicians had just asked for help from a woman her own country would not allow to be a professor. To see why they had no other choice, we have to go back to Erlangen, to a lecture hall at the turn of the century, where among 986 students sat exactly 2 women. One of them, auditing mathematics lectures, she was legally barred from attending as a student, entirely certain, against all available evidence, that she belonged there. Emmy Noether was born on March 23, 1882, in Erlangen, into a house where mathematics was the family business. Her father, Max Noether, was a respected professor of mathematics at the university there, a specialist in the geometry of curves and surfaces. Colleagues came to dinner. Problems were discussed at the table. By every account, she was a warm, unremarkable child. Nearsighted, cheerful, said to have a slight lisp, who showed no early signs of being a prodigy. One family story survives of a children's party where a puzzle had been set out to entertain the guests, and small Emmy was the only child who solved it. Beyond that, nothing. No legend of the 5-year-old doing calculus. She danced, she cooked, she went to the schools that girls were sent to. And here is the thing you have to understand about those schools. They were the whole of what her country intended for her. Germany at the turn of the century was arguably the greatest scientific nation on earth, and it had arranged its education system so that a girl could not attend the schools that prepared students for university. The doors were not merely difficult, they were closed by design. A young woman of ability had exactly one respectable intellectual path available, and Emmy dutifully walked it. She trained to become a teacher of languages, and in 1900 she passed the Bavarian state examinations, qualifying her to teach English and French at schools for girls. She was 18 years old, and she held in her hands the highest credential her society was prepared to give her. She never used it. Instead, that same year, she began appearing in the lecture halls of the University of Erlangen, not as a student, because women could not be students, but as an auditor, a guest, permitted to sit and listen only if the professor teaching each individual course gave his written consent. Some professors gave it, some did not. The university's academic senate had declared just a few years earlier that admitting women would overthrow all academic order, so she sat where she was tolerated, in rooms filled with young men who had walked in through the front door of the system, and she took notes on mathematics. In the whole university that year, there were 986 students. Exactly 2 were women. Think, for a moment, about the arithmetic of persistence involved. She had no guarantee that any of it would count for anything. There was no position waiting at the end, no degree. In the beginning, not even the right to take examinations. Every term, permission had to be asked again. Every course was a favor. She did this for 4 years, years in which the only currency she earned was the mathematics itself. And when the rules finally changed in 1904, and the university opened proper enrollment to women, she was ready. She matriculated at Erlangen, and in 1907, at the age of 25, she completed her doctorate summa cum laude, with highest honors, under a mathematician named Paul Gordon. Gordon matters to this story, because he represents everything Emmy Noether would eventually leave behind. He was called the King of Invariant Theory, and his kingdom was computation. His papers were oceans of formulas, page after page, of explicit symbolic labor, and the doctoral thesis he set for Emmy was exactly in that style. She computed, by hand, a system of 331 invariant expressions, belonging to a particular class of mathematical objects. It was heroic, meticulous, exhausting work, and she came to despise it. In later years, she dismissed her own thesis in a single syllable of German, Mist, a word that translates, politely, as dung. There is a famous story about Gordon that explains why. When David Hilbert, in 1888, had solved one of the central problems of invariant theory, not by computing anything, but by proving abstractly that the answer had to exist, Gordon had protested, "This is not mathematics, this is theology." That one sentence marks a border in the history of thought. The old mathematics of calculation on one side, the new mathematics of structure on the other. Emmy Noether was trained on the old side of that border. She would cross it, and then she would move the border itself, and by the end of her life, the abstract, structural style that Gordon called theology would simply be called algebra, and she would be more responsible for that than any other human being. But all of that lay ahead. What actually happened after the doctorate is this: nothing, no job. There was no job that could legally exist for her. A doctorate in hand, among the most capable mathematicians in Germany, she stayed in Erlangen for the next 7 years, and worked without any position and without any pay, helping her aging father with his lectures, supervising doctoral students unofficially, and publishing research of steadily growing power under her own name. Slowly, the people who could read that work began to notice it. Her reputation travelled the one way it could, through the mathematics itself, until it reached Göttingen, where, as we have seen, 2 men had run into a problem about invariance that was beyond even them. So in the spring of 1915 came the letter and the move, and then, almost immediately, the fight. Hilbert wanted Emmy Noether on the Göttingen faculty. To teach officially in a German university required a credential called the habilitation, a kind of second doctorate, and Hilbert proposed that she be granted the right to pursue it. The mathematicians and scientists were largely with him, but the decision belonged to the wider philosophical faculty, which included the historians and philologists, and there the proposal met a wall of refusal. The objections were not about her work. Nobody questioned her work. The objection that has come down to us, spoken in one of those faculty meetings, was this: what will our soldiers think when they return to the university and find that they are expected to learn at the feet of a woman? It was 1915. The soldiers in question were dying by the tens of thousands in the trenches of the First World War, and the faculty of Göttingen was defending them from the possibility of a female lecturer. Hilbert's reply has outlived every man who voted against her. "Gentlemen," he said, "I do not see that the sex of the candidate is an argument against her admission. We are a university, not a bathhouse." He lost. The vote went against her, and the ministry in Berlin confirmed the refusal. And here the story takes the turn that tells you who these people actually were. Hilbert simply ignored the outcome in practice. Courses began appearing in the Göttingen catalogue listed under his name, Professor Hilbert, Mathematical Physics, with a small printed note, with the assistance of Dr. E. Noether. Hilbert would not appear. Emmy Noether taught the courses. Everyone knew. The students knew, the faculty knew, the administration knew, and the fiction was maintained on paper for years, so that one of the great mathematicians of the 20th century could stand at a blackboard she was officially forbidden to stand at, teaching under a borrowed name, for no salary whatsoever. She lived on a small inheritance, and on almost nothing. She ate at a cheap boarding table. Witnesses from those years describe a woman entirely without bitterness, loud, warm, argumentative in the joyful way of someone who loves the argument itself, walking students through the streets of Göttingen after seminars, talking mathematics through the rain, oblivious to her coat. Her students would later be called the Noether boys, young men from across Europe and beyond, who came to orbit a teacher the university would not pay. Hold this picture in your mind, because the whole story turns on it. In 1915 and 1916 and 1917, while the war ground on and the faculty debated what soldiers would think, the person to whom the deepest problem in physics had been handed was teaching under someone else's name, for free, in a town that would not have her. And in those same years, in that same situation, she was quietly taking apart the problem Hilbert and Klein could not solve, not patching it, not repairing the energy theorems of general relativity. Something much stranger, she was discovering why they could not be repaired, and in the process, discovering what every conservation law in the universe had been trying to tell us all along. To understand what she found, we first have to understand exactly what was in danger. We have spoken of energy conservation as physics' most sacred rule. But rules like that are not born sacred. They are made sacred, slowly, by 2 centuries of evidence, argument, and failure. So before we open her 23 pages, we need to spend a little time with the rule itself, where it came from, who fought over it, and why by 1915 no physicist on Earth was willing to give it up. Because only when you feel the full weight of that rule can you feel what it meant for one woman to explain it. Every rule in physics has a biography, and the biography of energy conservation begins with an argument about what survives a collision. In the late 1600s, the philosopher and mathematician Gottfried Wilhelm Leibniz noticed something in the way moving bodies trade motion. The followers of Descartes insisted that what nature preserves is quantity of motion, roughly mass times speed. Leibniz argued that they were tracking the wrong quantity. The thing that behaves lawfully, he claimed, is mass times the square of speed, a quantity he called vis viva, the living force. Double a body's speed, and this living force does not double, it quadruples. It was the first clear sighting of the thing we now call kinetic energy, and it set off a dispute that ran for decades, because at the time, no one could say which bookkeeping was the true one. The person who settled it deserves a moment of your night. Émilie du Châtelet was a French marquise of the early 1700s, a physicist and mathematician in an age when France, like Germany 2 centuries later, had no place for her. She is remembered, when she is remembered at all, for translating Newton's great book into French, in an edition still used today. But she did far more than translate. She took up the vis viva dispute, and she pointed to an experiment performed by a Dutch scholar named Willems Gravesand, who had dropped brass balls into soft clay from different heights. If motion's true measure were simply mass times speed, a ball moving twice as fast should press twice as deep. It does not. It presses 4 times as deep, 3 times the speed, 9 times the depth. The clay was recording the square of the speed. The clay was voting for Leibniz. And du Châtelet assembled the argument, the mathematics, and the evidence into a case that helped carry the concept of energy into the mainstream of physics. A woman standing at the source of energy conservation. A woman, as we will see, standing at its explanation. The symmetry of that is almost too neat, and it is true. For the next century, energy remained a specialist's tool, useful in mechanics, but not yet a law of the universe. The transformation came in the 1840s, and it came from 3 directions at once, none of them from the center of the physics establishment. Julius Robert Mayer was a young German doctor, serving as a ship's physician on a voyage to the tropics. Bleeding patients in the East Indies, standard medicine at the time, he noticed that their venous blood ran brighter red than it did in northern latitudes, and he reasoned his way to an extraordinary conclusion. In the heat of the tropics, the body burns less fuel to keep warm, so less oxygen is drawn from the blood. Heat, motion, and the chemistry of food, he decided, must all be one currency, convertible at fixed rates, with the total always preserved. He came home possessed by the idea and spent years being ignored. His first paper was rejected, his claims dismissed as the enthusiasm of an amateur. At almost the same moment, in Manchester, a brewer's son named James Prescott Joule was performing some of the most patient measurements in the history of science. He stirred water with a paddle wheel driven by falling weights and measured the temperature rise, a rise so small that his thermometers, the finest of the age, could barely read it. Falling weight in, warmed water out, and always at the same exchange rate. Mechanical work was becoming heat at a fixed price. Joule announced his results and was, at first, politely disbelieved. And in 1847, a young Prussian physiologist named Hermann von Helmholtz drew the threads together in a treatise on the conservation of force, arguing on general grounds that in all of nature, mechanics, heat, electricity, magnetism, chemistry, even living bodies, one single quantity is shuffled from form to form and never created, never destroyed. There is a story told about Joule that may have been polished by a century of retelling, but it is too perfect to leave out. On his honeymoon in the Alps, the story goes, he brought along an enormous thermometer and spent part of the trip measuring the temperature of waterfalls, at the top and again at the bottom. His reasoning was pure conservation. The water that falls loses height, and the energy of that fall has to go somewhere. So the water at the bottom of a cascade should be very slightly warmer than the water at the top. He was right, of course. The warming is real, though far too small for his instrument to have caught in the spray of an alpine waterfall. That is the kind of person the law recruited, a man who could not stand under falling water without hearing the ledger being balanced. Within a generation, this had hardened from proposal into bedrock. The first law of thermodynamics, physicists came to call it. Energy can change costume, chemical to thermal, thermal to mechanical, mechanical to electrical. But the total in a closed system is fixed. It worked in the steam engines that were rebuilding civilization. It worked in the chemist's flask. It worked, astonishingly, in the sky. When 19th century physicists ask what feeds the sun, every candidate answer was disciplined by the same iron accounting. The rule survived every test that a century of industrial, chemical, and astronomical science could throw at it. No exception was ever found. None has ever been found since. You have lived your entire life inside this law, and it has never once let you down. Every heartbeat, every step, every degree of warmth in your room tonight is energy that arrived from somewhere, exactly and to the last decimal, on the books. The rule became so trusted that institutions built walls around it. As early as 1775, before the law was even properly formulated, the French Academy of Sciences had grown so weary of designs for wheels that turn forever that it announced it would no longer examine any claimed perpetual motion machine. Patent offices around the world eventually adopted the same posture. To this day, a perpetual motion claim faces a demand no other invention faces: show us a working model. And in 2.5 centuries, no model has ever worked. Think about what that means. Human ingenuity has assaulted this one law with more sustained inventive effort than perhaps any principle in science. Every clever gearing, every hidden magnet, every overbalanced wheel that a hopeful mind could devise, and the law has not bent once. But now notice something strange about all of this, something so obvious that it hid in plain sight for 200 years. Everything we have described is evidence that the books balance. None of it is a reason why. Mayer showed that heat and work sit in the same ledger. Joule measured the exchange rate to 4 decimal places. Helmholtz argued that the ledger covers everything. The patent offices established that the ledger cannot be cheated. And in all that time, through all that brilliance, essentially nobody asked the question a child would ask. Why is there a ledger at all? Why should the universe keep books? Physics could tell you with exquisite precision that energy is conserved. It could not tell you why energy is conserved, could not even tell you what kind of fact that was. Was it a brute decree, written into matter for no reason? Was it a habit the universe happened to have? The law stood like a wall in the middle of science, and nobody ever asked why the books balance. Because what could the answer even look like? There was one more strange thing, noticed only by the sharpest eyes. Energy was not alone. Physics had, by the late 19th century, a small family of these unbreakable bookkeeping rules. Momentum, the total push of moving bodies in a given direction, was conserved. That had been known since Newton, and it held in every collision ever measured. Angular momentum, the total amount of turning, was conserved. Skaters and planets obeyed it alike. Three great ledgers, each absolute, each unexplained, each apparently independent of the others. Why three? Why these three? Nothing in physics connected them. They were three separate miracles, and science, which exists to dissolve miracles, had simply learned to use them and stopped noticing how strange they were. This, then, is what stood in the balance in Göttingen in 1915. Not a formula, a covenant. The one promise nature had kept without exception since the first measurements were made, and the newest, most beautiful theory in the history of gravity could not seem to keep it. When Hilbert reached into general relativity for the energy ledger and found fog, he was not fumbling a technical detail. He was standing at the point where physics' deepest trust met physics' deepest theory, and finding that they did not fit. Here is what nobody in Göttingen yet understood, what nobody on Earth understood. The reason the ledgers existed, the reason there were exactly the ledgers there were, and the reason Einstein's theory treated them so strangely, were all one reason. A single fact, hiding underneath 2 centuries of physics, connected the skater and the steam engine and the misbehaving mathematics of curved spacetime. Emmy Noether was about to find it, but she would not find it by studying energy, or heat, or gravity. She would find it inside an idea that most people have never heard of, a way of writing the laws of nature that physicists had been quietly using for a century and a half, a formulation so elegant that it feels less like machinery and more like a secret. To follow her, we need to learn that secret language ourselves. It begins, of all places, with a beam of light taking the fastest road through a window pane, and with a question that sounds almost mystical. How does the light know which road is fastest? In 1662, the French mathematician Pierre de Fermat noticed something about light that should not have been possible. It was already known that light bends when it passes from air into water or glass. That is why a straw in a glass of water looks broken at the surface. The bending follows a precise rule measured decades earlier. What Fermat discovered is what the rule amounts to. Out of all the paths a ray of light could take from a point in the air to a point under the water, every conceivable dogleg and detour, the path it actually takes is the one that gets it there in the least time. Not the shortest path in distance, the fastest path in time, given that light moves more slowly in water than in air. There is a modern way to feel this. Picture a lifeguard on a beach who sees a swimmer struggling out in the water, off to one side. The lifeguard runs faster on sand than she swims in water. So the quickest rescue is not the straight line to the swimmer. That spends too long in the slow water. Nor is it running along the beach to the point directly opposite the swimmer. That makes the total trip too long. The quickest route slants. A longer run on the fast sand. An angled cut through the slow water. Work out the geometry of that optimal slant, and you get exactly the rule by which light bends at the surface of a pond. Light behaves like a perfect lifeguard, every time, at every surface on Earth. Which raises a question that sounds less like physics than like mysticism. How does the light know? A ray entering your window tonight bends at the glass precisely as if it had surveyed every possible route, computed the travel time for each, and selected the winner. A beam of light does not have a brain, it does not scout ahead, and yet the path it takes is always, without exception, the optimal one. Fermat's principle worked flawlessly. and explained nothing about itself, and it left behind a suspicion that would haunt physics for centuries, that beneath the push and pull picture of nature, there might be another picture entirely, in which the world behaves less like a machine and more like an optimizer, as if every process in nature were, in some sense we do not understand, choosing the best available option. In the 1740s, that suspicion became a program. A French mathematician named Pierre-Louis Moreau de Maupertuis proposed that all of mechanics, not just light, but matter, motion, everything, obeys a principle of the same shape. He defined a quantity he called action, and he claimed that in every natural process, nature spends this quantity as thriftily as possible. Nature is economical, he declared. In her every operation, the action is the least it can be. Maupertuis, it must be said, was rather grand about it. He thought he had found mathematical proof of the wisdom of the Creator, an argument for God, written in mechanics. The theology did not survive. The mathematics did. The great Leonhard Euler, the most prolific mathematician who ever lived, took Maupertuis' half-formed idea and made it rigorous. And then, over the following decades, an Italian-born mathematician in Paris, named Joseph-Louis Lagrange, rebuilt the whole of mechanics on top of it. Lagrange's book, The Analytical Mechanics of 1788, is one of the strangest masterpieces in science, and he was vain about it in the most wonderful way. In the preface, he boasts that the reader will find no diagrams whatsoever in his book, not one figure, in a book about motion. Mechanics in his hands had stopped being about pictures of pulleys and orbits and become pure mathematics. Write down one master expression for your system, turn a crank, and the equations of motion fall out. 50 years later, the Irish mathematician William Rowan Hamilton polished the idea into the form physics still uses, and the result is called the principle of stationary action, though everyone, with a small physicist's imprecision, still says least action. Here is what it says, and I promise you, this is the last piece of machinery we need before Emmy Noether's theorem, because this is the machinery her theorem runs on. Take any physical system, a thrown stone, a swinging pendulum, a planet, eventually even a field filling all of space. Now imagine every history that system could conceivably have between two moments. Every path the stone could take from your hand to the ground, the sensible arc, and the absurd zigzags alike. For each imaginable history, the rules assign a single number, computed from how the energy of motion and the energy of position trade off along the way, added up over the whole journey. That number is the action. One history, one number, a score, if you like, for every possible way the world could get from here to there. And the principle says, the history that actually happens is the one whose score is stationary, the one sitting at the balance point, where every tiny variation of the path leaves the score, to first approximation, unchanged. Nudge the true path slightly, and the action does not care. That indifference is the signature of reality. Out of the infinity of conceivable histories, nature's is the one you cannot improve by any small adjustment. If that feels like an oddly backward way to state a law, notice what it buys. Newton's way of doing physics is local and effortful. At each instant, tally every force on every body, compute every acceleration, step forward, repeat. The action way is global and serene. One quantity, one principle, and the entire history of the system unfolds from it at once. And the deepest fact of modern physics is that this is not a curiosity confined to old mechanics. Every fundamental theory we possess can be written this way, and at the highest levels of physics is written this way. Maxwell's electromagnetism flows from an action. Einstein's general relativity flows from an action. Hilbert himself, in the frantic November of 1915, found the theory's action, while Einstein was finding its equations. The entire standard model of particle physics, the most precisely tested construction in the history of human thought, is specified, completely, by writing down its action. When physicists dream of a final theory, the dream has a definite shape. It is the dream of writing down one last action. The principle of least action is not a tool in physics workshop. In a real sense, it is the workshop. Richard Feynman liked to tell the story of how he met this idea, and it is worth retelling, because it captures the feeling of initiation that surrounds it to this day. When Feynman was in high school in New York, his physics teacher, a Mr. Bader, noticed that the boy was bored to death and took him aside after class one day. Bader did not give him extra homework. He told him something, that there is a way of doing all of mechanics in which you never mention forces at all. You compute one quantity along each imaginable path, and nature takes the path that holds that quantity stationary. Feynman would say, decades later, that he found it the most remarkable thing he had ever been told, and that he never recovered from it. The man who would go on to rebuild quantum theory, and who found, in doing so, that even quantum particles are best understood through the action, as if they genuinely sample every available path, and the familiar world is what survives the sampling, traced it all back to a teacher who let him in on physics' secret formulation. And it is a kind of secret. You can go through years of schooling, learn all about forces and energy and acceleration, and never once hear that underneath all of it, physics keeps a single set of master books written in one quantity almost nobody outside the field has heard of. By 1915, then, this was the language in which the deepest physics was conducted, and it is the language Emmy Noether worked in when Göttingen handed her the energy crisis. And now we can finally say precisely what she was looking at. General relativity was an action theory, like everything else. Its conservation troubles had something to do with what happens to an action when you change your description of space and time. The question she needed to answer was a question about sameness. What happens to physics when you transform a system's action, and the action does not notice? What does the world owe you when there is something you can do to it that leaves its master score unchanged? To ask that question properly, we need one more word, the most beautiful word in physics, and one of the most misunderstood. That word is symmetry, and what it actually means is nothing like what most of us were taught. The word symmetry, in everyday speech, means something like balance or prettiness. A face is symmetric. A cathedral is symmetric. Physics means something sharper, and the sharpest statement of it belongs to Hermann Weyl, a Göttingen mathematician, a colleague and admirer of Emmy Noether, and the man who would one day deliver her eulogy. A thing is symmetrical, Weyl said, if there is something you can do to it, so that after you have done it, it looks the same as it did before. Sit with that definition for a moment, because everything that follows tonight lives inside it. Symmetry is not a property of stillness. It is a property of survival under change. To find the symmetry of a thing, you do not look at it. You act on it, and then check what your action failed to change. Take a plain circle drawn on a page. Rotate it about its center by 10 degrees. It looks the same. Rotate it by 17 degrees, or by 1/100th of a degree, or by any angle you like, however small. It looks the same. The circle survives an entire continuous family of rotations, a smooth, unbroken range of transformations, as fine-grained as you please. Now take a snowflake, with its 6 arms. Rotate it by 60 degrees, and it looks the same, but rotate it by 10 degrees, and it visibly does not. The snowflake's symmetry is real, but discrete. It survives only certain special jumps, 6 clicks in a full turn, like a wheel with notches. The circle's symmetry is continuous. It survives arbitrarily small nudges. Hold on to that distinction between smooth symmetries and click symmetries. Noether's theorem, when we finally open it, will speak only about the smooth kind, and late tonight, when we meet the click kind again, the difference will turn out to matter enormously. A mirror gives you another click symmetry. Reflect a butterfly left to right, and it looks the same. But there is no such thing as reflecting it only slightly. Reflection happens entirely, or not at all. So objects can carry whole families of symmetries, some continuous, some discrete, and mathematicians learned in the 19th century to treat those families as objects in their own right. The Norwegian mathematician Sophus Lie built an entire theory of continuous symmetries, the smooth families, like the circle's rotations, and that theory, Lie theory, remains one of the load-bearing structures of modern mathematics and physics alike. And recall Felix Klein's manifesto from Erlangen: a geometry simply is the study of what survives a family of transformations. By the time Emmy Noether reached Göttingen, asking what stays the same under what you can do was no longer a parlor observation. It was among the most developed instruments in mathematics, and she was one of its living masters. Now comes the move that turns this from geometry into physics, and it deserves to be taken slowly. Objects can have symmetries, but laws can have symmetries too. Ask Whale's question, not about a snowflake, but about the rules of nature themselves. What can you do to the world that leaves the laws of physics looking the same? Here is one thing you can do. Wait. Run an experiment tonight. Drop a stone. Time its fall. Now do the identical experiment tomorrow night. Every measurement, to the limits of precision, comes out the same. The stone does not fall differently on Thursdays. Whatever the laws of physics are, shifting the entire experiment in time by a day, a year, or a billion years leaves them looking the same, and not just by whole days, by an hour, a second, any sliver of time however small. The laws survive a continuous family of time shifts, the circle's kind of symmetry, not the snowflakes. Here is another thing you can do. Move. Perform your experiment in London, then perform it in Tokyo, then, if you can manage it, in the Andromeda Galaxy. The laws are indifferent. Astronomy is our deepest witness here. When we read the light of galaxies, billions of light years away, we find atoms making exactly the transitions they make in our laboratories, to exquisite precision. Hydrogen is hydrogen everywhere we have ever looked. Shift the whole world sideways by any distance, in any direction, and the laws look the same. And you can turn, face your apparatus north, then west, then any angle in between. No experiment ever performed has detected a preferred direction in the laws of physics. Rotate the world, and the laws look the same. And there is one more, subtler thing you can do, first understood by Galileo. Get moving, smoothly. Seal yourself in the cabin of a ship gliding on calm water, his example, and no experiment inside the cabin will tell you whether you are moving or moored. Uniform motion leaves the laws looking the same. Count what we have gathered. You can slide the world in time. You can slide it along 3 independent directions of space. You can rotate it about 3 independent axes. You can set it gliding in 3 independent directions. 1, plus 3, plus 3, plus 3, 10 distinct continuous families of transformations that the laws of nature survive. 10 independent answers to Whale's question. 10 things you can do to the universe, after which it looks the same. Physicists call this 10-fold family the symmetry group of space-time, and it is as fundamental a fact about our world as any measurement in any laboratory. Keep that number 10 in your pocket. Before tonight is over, it will match another number 10, and the match will not be a coincidence. It will be the whole story. I want you to feel these symmetries rather than merely list them, so come with me for a moment. Imagine yourself floating in a place with no landmarks at all. Deep intergalactic space, if you like. The blackness between the galaxies. Nothing within a million light years of you. You hold a clock in one hand and a ruler in the other. Now drift 1 kilometer to your left. Look around. Nothing about the world has changed. Not because you failed to move, but because the world had nothing there to make one place different from another. Turn 90 degrees. The blackness turns with you, indistinguishable. Wait an hour, holding still. The hour passes, and no experiment you could perform, no swing of a pendulum, no tick of your clock, no spectrum of any atom you carry, comes out differently than it would have an hour before. You begin to notice something almost physical about the sameness. It is not emptiness you are feeling, it is structure. The world is not failing to respond to you, it is responding identically, everywhere, every when, in every direction, and that identical response is itself a fact about reality, perhaps the deepest fact there is. You are floating inside the symmetry of the universe, the way a fish floats inside water. It is invisible, precisely because it is everywhere. And now, give yourself the gentlest push, and glide. You are moving. By any outside reckoning, distance is slipping past, and yet inside your own drifting frame, every experiment behaves exactly as it did at rest. Your clock ticks at its rate. A dropped bead floats calmly beside your hand. Galileo's ship has become your body, and the 10th symmetry closes around you as quietly as the other 9. Nothing you can do here, wait, step, turn, glide, will make the universe respond differently. It looks the same. One caution before we go on, because precision here is the whole game. When we say the laws are symmetric, we are not saying the world is symmetric. The world is conspicuously lopsided. The sun is over here and not over there. You are in your bed and not on the ceiling. This galaxy spins one way and not the other. Situations break symmetries constantly. That is why there is a here and a now and a you. The claim is about the rules, not the arrangement of the pieces. Chess played in Buenos Aires follows the same rules as chess played in Oslo. Even though no two boards anywhere show the same position, the board is particular, the rulebook is symmetric. Physics, by 1915, knew its rulebook was symmetric in at least those 10 continuous ways, and regarded the fact as a pleasant, faintly philosophical footnote. Nice to know. Good for the tidiness of the equations. Useful nowhere. So now the stage is fully set, and look at what history had gathered onto it. A master language. The action. The single score that encodes a theory's entire content. A master question. What can you do to a thing so that it looks the same? A crisis. The most trusted law in science gone soft inside the greatest theory of the age. And a single person, standing where all three met, the finest invariant theorist alive, unpaid, untitled, teaching under a borrowed name, in the one town on earth where the crisis lived. In the summer of 1918, Emmy Noether connected them. What she proved fits in a sentence. What it means has not stopped unfolding in 100 years. And once you see it, the world genuinely does not look the same afterward. It is time to open the 23 pages. On July 26, 1918, the Royal Society of Sciences in Göttingen convened one of its regular sessions, and a paper was read into its proceedings under the title Invariante Variationsprobleme, Invariant Variational Problems. 23 pages. The author was Emmy Noether. The man presenting it was Felix Klein, and he was presenting it for a reason that belongs in the story's permanent record. The author could not present her own paper, because the Royal Society of Sciences did not admit women, and never would while she lived. The deepest result about the laws of nature ever proven to that point entered the world, read aloud by someone else, on behalf of a scientist who was not allowed in the room as a member. While outside, that same July, the German army's last offensive was collapsing on the Western Front, and the world that had built Göttingen was ending. Almost nobody noticed the paper. It would take physics decades to understand what had happened that day. Here is what had happened. The paper contains 2 theorems. The second one answers Hilbert's question about general relativity, and we will come to it. But the first theorem, the one the world now simply calls Noether's theorem, says this. Take any physical system described by an action, that single master score we learned to read 2 chapters ago. Suppose the action has a continuous symmetry, something you can do to the system, smoothly, by any amount, however small, that leaves the action unchanged. Then the theorem states that the system's equations of motion automatically contain a conserved quantity, some definite, calculable thing whose total value never changes as the system evolves. And the theorem is constructive. It does not merely promise that a conserved quantity exists somewhere. It hands you the formula. Feed in the symmetry, and the machinery outputs the conserved quantity, explicitly, every time. One continuous symmetry in, one conservation law out. And the correspondence runs in reverse as well. Where you find a conserved quantity, a continuous symmetry stands behind it. The two are not neighbors. They are the same fact, written in two vocabularies. Now watch what this single sentence does to everything we have built tonight. The laws of physics are symmetric under shifts in time. Run the experiment today or tomorrow, and the action does not notice the difference. Feed that symmetry into Noether's machinery, and out comes a conserved quantity. That quantity is energy. Energy conservation, the covenant, the load-bearing wall, the rule that survived 2 centuries of steam engines and starlight, and every perpetual motion hustler who ever filed a patent, is the shadow cast by the sameness of time. The books balance, because tomorrow's rules are today's rules. That is the reason. That was always the reason. When we asked, 2 chapters ago, why the universe keeps books at all, the question a child could ask, and no scientist could answer, this is the answer physics had been unable to imagine for 200 years. Energy is conserved because nature does not care what time it is. And you can feel why the connection holds, without a single equation, by imagining its absence. Suppose the laws of physics did drift with time. Suppose, say, that gravity ran slightly weaker on Tuesdays than on Fridays. Then you could build a very profitable machine. Pump a reservoir full of water to the top of a hill on Tuesday, when lifting is cheap, and let it fall back through turbines on Friday, when falling pays more. Around and around, week after week, the machine would mint energy from nothing, a perpetual motion machine, powered entirely by the calendar. The reason no such machine can exist is that there is no such calendar. The cost of lifting and the payout of falling are fixed by laws that do not know what day it is. 2.5 centuries of failed perpetual motion machines were not 2.5 centuries of insufficient cleverness. They were 2.5 centuries of experimental proof that time has no seams, that the universe will not let you buy low on Tuesday and sell high on Friday, because its Tuesdays and its Fridays are identical. The patent offices, it turns out, were enforcing the symmetry of time without knowing it. The laws are symmetric under shifts in place. London physics is Tokyo physics is Andromeda physics. Feed that in, and out comes a second conserved quantity, momentum. The unstoppable coast of a moving body through empty space is the shadow of the sameness of space. Momentum is conserved because nature does not care where you are. The laws are symmetric under rotation. No compass direction is written into the rules. Feed that in, and out comes angular momentum, the conserved quantity of turning. The skater's spin, the planet's steady orbital sweep, shadows of the fact that nature does not care which way you face. And the laws are symmetric under gliding, Galileo's ship. Feed that in, and out comes the least famous of the family, a conservation law almost nobody teaches. The center of mass of an isolated system moves in a straight line at constant speed, and nothing internal can ever change that. A crew can run about the decks of their sealed ship however they please. The ship's balance point sails serenely on, unbribable. Count them now, as promised. 1 symmetry of time, 3 of space, 3 of rotation, 3 of gliding, 10. 10 continuous symmetries of space-time, and classical physics possesses exactly 10 great conserved quantities. 1 energy, 3 components of momentum, 3 of angular momentum, 3 encoding the steady drift of the center of mass. 10 and 10. The match is perfect, And after July of 1918, physics finally knew it was not luck. It is a dictionary. Every entry on one side has exactly one partner on the other, and Noether's theorem is the dictionary's grammar. Let the strangeness of the old situation land, now that it has dissolved. For 2 centuries, physics had held 3 separate miracles: energy, momentum, angular momentum, each absolutely conserved, each unexplained, each apparently unrelated to the others. 3 brute facts, 3 commandments without a lawgiver, and the theorem revealed them to be 3 verses of 1 sentence. The universe does not care when, does not care where, does not care which way. The miracles were never separate, and they were never miracles. They were symmetry, seen from the inside, the whole time. This is why the discovery could not have come from another experiment, however precise. Experiments had confirmed the ledgers 10,000 times over. What was needed was someone who could look underneath the ledgers, someone fluent enough in the mathematics of invariance to ask what the bookkeeping was made of. It was needed, in other words, that the question of the age fall into the hands of precisely the person the universities of Europe had spent 30 years refusing to employ. There is a distinction buried here that I want to hold up to the light, because it explains why this result stands apart, even among the treasures of physics. Almost everything in science is a theory. A theory is a proposal about the world, and the world gets a vote. Newton's gravity was a magnificent theory, and the world eventually voted against it in favor of Einstein's. And someday, the world may vote against Einstein's in favor of something deeper. But Noether's result is a theorem. It is mathematics, not proposal. It says, whatever the laws of nature turn out to be, Newton's, Einstein's, the quantum theories, or theories not yet dreamed, if they can be written as an action, and if that action has continuous symmetries, then conservation laws of the corresponding kind must follow. That covers every fundamental theory humanity has ever written down, and every one currently imagined. Theories are mortal. This is a statement about all possible theories of a very broad kind, and so it does not die with any of them. A theorem is forever. Physics has overturned itself twice since 1918. Relativity rewrote space and time. Quantum mechanics rewrote matter and certainty. And Noether's theorem passed through both revolutions untouched, because it was never a claim about what the world is made of. It is a claim about what lawfulness itself entails. Einstein read the paper. In the days after its presentation, he wrote to Hilbert, and you can hear, under the formality, a man startled by quality. On receiving the new work from Fräulein Noether, he said, he found it once again a great injustice that she could not lecture officially. He would repeat the judgment in stronger terms for the rest of his life. Klein presented her results with open admiration. Inside the small circle who could read what she had written, there was no doubt about what she was. Outside that circle, the fiction held no title, no salary, no membership. Her name absent from the catalogue, while her theorem sat quietly in the proceedings, waiting for physics to grow into it. And physics would grow into it in ways nobody in that room could have imagined, because the theorem's reach turned out to extend far beyond the 10 symmetries of space and time. But before we follow it into the strange interior spaces of the quantum world, we should do something simpler. We should go outside. Because the extraordinary thing about this theorem, the thing that separates it from nearly every other great result in physics, is that its evidence is not locked in any laboratory. It is running continuously, in plain sight, in every playground and kitchen and night sky you have ever looked at. You have been watching Noether's theorem operate your entire life without knowing its name. So let us step back for a moment, gather what we have, and then take the theorem for a walk through the ordinary world, starting with a spinning chair, a bag of groceries, and a dying star. Let us step back for a moment and stack the pieces we have gathered, because we have crossed the midpoint of a large idea, and it deserves to be seen whole. Physics keeps a set of ledgers: energy, momentum, angular momentum. that 2 centuries of measurement could confirm but not explain. Physics also writes its deepest laws in a single master quantity, the action, a score assigned to every possible history of the world. And the laws, so written, are symmetric. There are 10 distinct continuous things you can do to the universe: wait, slide, turn, glide, after which it looks the same. In July of 1918, Emmy Noether proved that these 2 facts are one fact. Every continuous symmetry of the action forces a conservation law into existence, and every conservation law is a symmetry wearing a disguise. The ledgers balance because the stage is featureless. That is the theorem. Now let us take it outside and watch it run the world. Start with a spinning chair. An ordinary office chair will do. Sit in it, push off gently, and hold your arms out wide as you turn. Now pull your arms in against your chest. You speed up. Nothing pushed you. No motor engaged. No force arrived from anywhere. You merely changed your shape, and the world instantly adjusted your spin. What you are feeling is a conservation law, enforcing itself in real time. Your amount of turning, your angular momentum, is fixed the moment your feet leave the floor, and angular momentum is built from 2 ingredients: how fast you turn, and how far your mass sits from the axis. Pull your mass inward, and one ingredient shrinks, so the other must grow to keep the total constant. The books must balance, so you accelerate. A figure skater is a person who has made an art form out of this bookkeeping. Arms and free leg flung wide into the spin, then drawn in tight along the axis, and the rotation blooms from a lazy turn to a blur. Elite skaters exceed 300 revolutions per minute, faster than the wheels of many cars on a highway, with no engine but geometry. And Noether's theorem stands quietly behind the whole performance, saying the one thing it always says: the skater spins up because empty space has no favorite direction. Rotational symmetry is the reason her spin is conserved. She is dancing with the sameness of the universe. Now hold that image and let me change its scale, because the universe performs the identical trick with instruments somewhat larger than a skater. Imagine a great star, far heavier than our sun, arriving at the end of its life. Like our sun, it rotates, slowly, patiently. Our own sun turns once in about 25 days, and a giant star turns in its own stately period. Then, in a single day of catastrophe, its core runs out of fuel and collapses, crushing a mass greater than the sun's into a sphere the size of a city, from something like 1,000,000 kilometers across to about 20. The star's core has done exactly what the skater did. It has pulled its arms in by a factor of tens of thousands, and so it must spin up by the matching factor. The result is called a neutron star, and neutron stars rotate at speeds the mind flatly refuses. The young pulsar at the heart of the Crab Nebula, the collapsed core of a star seen exploding in the year 1054, turns 30.2 times every second. The fastest known, a pulsar named for its catalogue entry, turns 716 times per second. A ball of matter, heavier than the sun, wide as a city, spinning faster than the blades of a kitchen blender. And the physics that requires this is the same physics that spun you in your office chair. One conservation law, one symmetry behind it, operating without modification from your living room to the corpse of a star. The theorem does not have a size. Come and feel it once, slowly, before we move on. It is dusk, and you are standing on one of those old playground merry-go-rounds, the flat steel disc with the curved handrails, and a friend has set you turning. You lean out, arms wide, hands on the cool rail, and the world wheels past at an easy, drowsy pace. Trees, fence, the first stars, trees again. Now draw yourself inward, hand over hand, toward the center. The change arrives smoothly and immediately. The wheeling quickens, the air moves faster against your face, and nothing has touched you. You feel the speed being paid out to you from somewhere, as if the spin were stored and you have moved closer to where it is kept. Then reach out again, arms wide, and the world obligingly slows. In and fast, out and slow, as many times as you like. You are operating the conservation of angular momentum with your own arms, trading shape for speed under a law that has no exceptions, on a steel disc built by someone who never heard of Emmy Noether. It does not have an era, either. 4 centuries ago, Johannes Kepler, staring at Tycho Brahe's tables of the planet Mars, extracted a strange regularity, now called his second law. The line from the sun to a planet sweeps out equal areas in equal times. When the planet is near the sun, it hurries. When it is far, it strolls. And the trade is exact. Kepler had no idea why. It was, for him, a pattern found in the data, numerology, that happened to be true. Tonight you know what he was looking at. Equal areas in equal times is nothing but the conservation of angular momentum, and behind it, the rotational symmetry of space. Our own Earth obeys it around you as you lie there. In early January, at its closest approach to the sun, the Earth moves at 30.29 kilometers per second. In early July, at its farthest, 29.29. Faster when close, slower when far. The areas exactly equal. A planet keeping Noether's books across the silence of 400 years and 150 million kilometers. And when a comet falls in from the outer darkness on a long ellipse, whipping around the sun and coasting back out for another century, same law, same symmetry, same theorem. Momentum runs its own department of the ledger. Every rocket that has ever flown through vacuum has flown on it. People sometimes puzzle over what a rocket engine pushes against in empty space, and the answer is nothing, and it needs nothing. The exhaust streams one way, carrying momentum. The ship must carry an equal amount the other way, because the total is fixed and the books do not close at the end of the day. They are closed at every instant, continuously, by the sameness of space itself. Far beyond the planets right now, the Voyager 1 spacecraft is coasting outward at about 17 kilometers per second, with its engines cold, and it will coast essentially forever, needing no fuel to keep its speed, because uniform motion is not a process that consumes anything. It is what the symmetry of space looks like when nothing interferes. And the family's forgotten member, the gliding law, is aboard every ship at sea tonight. A freighter's crew can shift every container in the hold, run laps on the deck, do anything an isolated system can do, and the ship's center of mass will not swerve by a millimeter for any of it. Isolated systems cannot steer themselves. That is the boost symmetry, collecting its due. And energy is the ledger you are made of. The warmth of your body right now is running at roughly 100 watts, about the old-fashioned light bulb's worth of glow, and every joule of it is accounted for. It arrived in your food, which stored the sunlight of the last growing season, which was minted by fusion in the core of the sun, which is spending gravitational capital, gathered when the solar system condensed from a cloud 4.5 billion years ago. Not one step in that chain created anything. Not one step destroyed anything. The energy warming your blanket tonight is old beyond imagining, transformed 1,000 times, lost never, because from the cloud's collapse to your heartbeat, the universe has not once cared what time it was. Look around your ordinary world, then, and see it briefly as the theorem sees it. A door swings on its hinges, angular momentum flows and balances. A child jumps from a rowboat, and the boat glides backward. Momentum, splitting the books 2 ways. Coffee cools, and the kitchen warms by exactly the difference. None of it is many laws. It is a few symmetries, casting long shadows. And yet, one item of the original assignment remains open, and it is the item that started everything. All of tonight's bookkeeping has assumed the stage itself holds still, that space and time are the fixed, featureless backdrop, whose sameness the theorem converts into law. But Einstein's whole revolution was the discovery that the stage does not hold still. Space and time bend, stretch, and flow. What happens to Noether's beautiful dictionary when the paper it is printed on starts to move? That was Hilbert's question in 1915, and it is time to hear her second answer, the stranger one. Remember why she was summoned. Not to explain skaters, and not to unify the ledgers of classical physics. Nobody in Göttingen knew those gifts were coming. Emmy Noether was brought in because energy conservation misbehaved inside general relativity, and Hilbert suspected the misbehavior was not a flaw, but a feature he could not prove. Her paper's second theorem is the proof, and it is, if anything, stranger and more beautiful than the first. Here is the heart of it, with no equations. The first theorem, as we have seen, runs on symmetries that form small, finite families. 1 knob for time shifts, 3 for space shifts, and so on. 10 knobs in all. General relativity's defining symmetry is not like that. Einstein built his theory on the demand that the laws keep their form under any smooth relabeling of space and time whatsoever. Not 10 knobs, but an infinity of them. A different adjustment allowed at every point of the universe independently. The theory's symmetry is not a small family of moves. It is an ocean of them. And Noether proved that when a theory's symmetry is that large, the character of its conservation laws changes kind. The bookkeeping identities still exist, but they become true automatically, as pure mathematics, in a way that no observation could ever contradict. Physicists translate her term as improper conservation laws. An ordinary, proper conservation law is a promise with content. Measure the energy now, measure it later, and the totals will agree, something that could conceivably fail, and never does. An improper conservation law is a sentence with the grammar of a promise and the content of a tautology. It holds, but it holds the way 0 equals 0 holds. If the distinction feels slippery, try it as banking. A proper conservation law is a real audit. The bank counts the money in the morning, counts again at night, and the two counts must match. A match the world could fail to deliver, and never does. An improper conservation law is a bank whose only rule is that the balance equals the balance. The auditor arrives, checks the rule, finds it holds perfectly, it cannot do otherwise, and goes home having learned nothing about the money. Both banks have spotless books. Only one of those books says anything about the world. General relativity, Noether proved, runs the second kind of bank wherever its infinite symmetry operates, and no cleverness of accounting can ever turn its identity back into an audit. Hilbert's fog was real, and it was structural. He had suspected exactly this, and could not prove it. She proved it, and in her paper she noted, with typical dryness, that her result confirmed what Hilbert had asserted. The assignment Göttingen's giants could not complete was completed, definitively, as the second item in a paper whose first item had already rewritten the meaning of physical law. But what does it mean, physically, for gravity's energy books to go improper? It means something that still unsettles physicists a century later. In general relativity, there is no observer-independent answer to the question of how much energy the gravitational field contains at a given place. Every formula ever proposed for the local energy density of gravity turns out to depend on the coordinates, on the map, not the territory. Choose your labels one way, and a stretch of empty space appears to hold gravitational energy. Choose them another way, and the same stretch holds none. Einstein's own favorite energy expression, applied to perfectly flat, perfectly empty spacetime, described in the wrong coordinates, cheerfully reports energy that is not there. The number moves when you change the map, and a number that moves with the map is not a physical thing. This does not mean gravity's accounting is lawless. In any small laboratory falling freely, inside a space station, in a plunging elevator, energy conservation holds exactly, locally, always. And for an isolated system viewed from far away, where spacetime flattens out, honest total energy definitions do exist. That is why physicists can state, meaningfully, that a pair of merging black holes once radiated 3 suns' worth of energy in a fraction of a second. What fails to exist is the universal, everywhere defined, observer-independent energy ledger that classical physics took for granted. Locally, the books are kept. Globally, in a curved and dynamic space-time, there is often simply no ledger to keep. And now follow this thread one step further, to the largest scale there is, because here the second theorem delivers its quiet shock. Noether's first theorem ties energy conservation to one specific symmetry, the sameness of time. Ask then, is our universe actually the same from one epoch to the next? It is not. The universe is expanding. It was denser yesterday than today, hotter a billion years ago than now, and the difference is not philosophy, it is measured. On the largest scales, the universe is not time translation symmetric, and Noether's theorem, read honestly, therefore declines to promise a conserved total energy for the cosmos. And the cosmos takes the theorem at its word. Light crossing the expanding universe stretches with the space it crosses. The photons of the cosmic microwave background, released when the universe was about 1100 times more compressed than today, have had their wavelength stretched by that same factor of 1100, and a photon's energy falls as its wavelength grows. Each of those photons has lost roughly 99.9% of the energy it was born with. That ancient light, emitted at the temperature of a star's surface, arrives today as a whisper of microwaves at 2.725 degrees above absolute zero, cooled not by giving its heat to anything, but by the stretching of the space it travelled through. Where did all that energy go? Noether's answer is that the question is malformed. It did not go anywhere, because the total energy of the expanding universe was never a quantity the theorem underwrote. No symmetry, no ledger, no missing entry. Meanwhile, dark energy, whose density stays constant while space itself grows, presents the mirror image strangeness. More space, more of it, with no account debited. The deepest bookkeeping rule in science turns out to be a local privilege of a universe that, patch by patch, hour by hour, looks the same, not a decree binding the whole of cosmic history. I should pause here for a warning, because this corner of physics has been badly misused. There is a line of talk that circulates online, which runs, physicists admit energy is not conserved in the expanding universe. Therefore, the conservation laws are negotiable. Therefore, machines that make free energy are possible, and are being suppressed. Every link in that chain after the first is broken. Energy conservation relaxes only where the time symmetry is genuinely absent, and the expansion of the universe is measurable only across millions of light years and millions of years. In your garage, in any laboratory, in any power plant, on any bench where a machine could ever be built, space-time is static to a precision beyond measuring. The symmetry holds, and the theorem's grip is total. A device on a workbench lives in a world where today is identical to tomorrow, and its books therefore balance, not as an observed habit that a clever gearbox might one day evade, but as a proven consequence of the sameness of its days. The universe's exception does not leak. There is no suppressed machine. There is a theorem, and the theorem is precisely why the patent offices have never been proven wrong. So the 1915 assignment closed with a verdict no one expected. The sacred law was neither broken nor saved. It was explained, and its jurisdiction was drawn on a map for the first time. Energy conservation reigns exactly where time is seamless, and abdicates exactly where it is not. That is a stranger, more precise, more honest answer than either Hilbert's fear or the old faith, and it set up the 20th century for a question with real teeth. If conservation laws are only ever as good as the symmetries behind them, what should a physicist do when a ledger appears to leak right here on Earth, in a laboratory, where the symmetry of time is beyond suspicion? Trust the books, or trust the experiment? Within a decade of Noether's paper, that exact dilemma arrived, in the decay of radioactive atoms. and the story of how physics answered it is one of the great dramas of the scientific 20th century, complete with a desperate letter, a dance in Zurich, and a wait of 26 years. The leak appeared in the humblest of places, the slow crumbling of radioactive atoms. Certain unstable nuclei decay by spitting out an electron, beta decay, physicists called it, and by the simplest reasoning in the world, every such electron should emerge with the same energy. The parent nucleus has a definite energy. The daughter nucleus has a definite energy. The electron should carry away exactly the difference, every time, like change from a fixed price. But from 1914 onward, measurements told a different story. The electrons came out with a continuous smear of energies, some fast, some slow, most somewhere in between, as if the fixed price were being paid in random, incomplete installments. For a while, physicists hoped the missing energy was hiding somewhere ordinary. Perhaps the electrons lost it on the way out, scattering through the material. In 1927, Charles Ellis and William Worcester closed that door with one of the most elegant measurements of the decade. They sealed a beta-decaying substance inside a calorimeter, a device that catches everything and converts it to heat, so that whatever energy the decays released, in any hidden form, would be captured and counted. If the full price was being paid, the heat would show it. The heat came out at 344,000 electron volts per decay, give or take 10%. The full price was 1,050,000. 2/3 of the energy was not hiding in the apparatus. It was leaving the universe of the measurable altogether. Decay by decay, atom by atom, the most sacred ledger in physics was failing to balance. On Earth, on a laboratory bench, where the symmetry of time was beyond all suspicion. Something had to give, and the question was what? And here, the two greatest quantum physicists of the age split, cleanly, along the fault line this whole night has been tracing. Niels Bohr was prepared to let the ledger go. He had tried once before. In 1924, with Kramers and Slater, he had proposed a quantum theory in which energy was conserved only on average, statistically, over many events, with individual atomic processes free to cheat. That idea had been executed within a year by experiment. Walther Bothe and Hans Geiger showed that in individual collisions between light and electrons, the books balanced event by event, not merely on average. Undeterred, faced now with beta decay, Bohr reached for the same heresy again. Perhaps, he suggested around 1930, in the strange interior of the nucleus, the law of energy conservation simply does not apply. He was even willing to speculate that the stars might shine on energy quietly minted from nothing. It is worth pausing on who this was. The founder of the quantum atom, the most influential physicist alive, proposing in cold seriousness that the first law of thermodynamics was optional. That is how bad the crisis was. Wolfgang Pauli, younger, sharper-tongued, and possessed of perhaps the most unforgiving physical instinct of his generation, thought this was close to madness. In a letter to Bohr, he delivered one of physics' great one-liners, "Let the stars radiate in peace." The ledger, Pauli was certain, does not fail. And if the ledger does not fail, then something unseen was walking out of those experiments, carrying the missing energy. It is the evening of December 4th, 1930, in Zurich, and Pauli is at his desk, writing a letter he knows is slightly scandalous. In Tübingen, the assembled experts on radioactivity, Lisa Meitner and Hans Geiger, among them, are meeting to confront the beta decay crisis, and they have asked for his thoughts. He begins with a joke, because he cannot help it. "Dear radioactive ladies and gentlemen." Then he lays it out. He proposes, he calls it a desperate remedy, that there exists in nature a particle nobody has ever seen, electrically neutral, unimaginably light, barely willing to interact with matter at all. In every beta decay, he suggests, one of these phantoms is emitted alongside the electron, and it carries away precisely the missing energy. The smeared-out installments are not incomplete payments, they are complete payments, split two ways, with one recipient invisible. He knows how it sounds. He admits in the letter that he does not dare publish the idea. He closes by begging the radioactive company's pardon. He cannot appear in Tübingen in person, because a ball in Zurich has made his presence here indispensable on the night of December 6th. It is perfectly in character, and somehow perfect for the story. The man rescuing the deepest law in science posts the rescue by mail, seals the envelope, and goes dancing. Privately, he was less breezy. To the astronomer Walter Bard he later confessed, "Today I have done a terrible thing, something no theoretical physicist should ever do. I have proposed something that can never be verified experimentally." He is said to have bet a case of champagne that his own particle would never be detected. Understand what he was actually staking and why. After Noether, energy conservation was no longer an isolated empirical habit that new physics might casually revise. It was welded to the sameness of time itself. To abandon the ledger in beta decay, one would have to believe that time's symmetry fails inside the nucleus, while holding perfectly everywhere else. Against that enormity, Pauli chose the smaller impossibility, an undetectable particle. It was, in the most literal sense, a wager on symmetry, the first great bet ever placed on Noether's theorem, made by a man betting against his own ability to ever collect. The particle got its name 3 years later, almost as a joke. Enrico Fermi, asked whether Pauli's particle was the same as Chadwick's newly found neutron, answered in Italian that no, Pauli's was the little neutral one, the neutrino. In 1934, Fermi built the first real theory of beta decay around it, mathematics of such quality that it stands, in refined form, inside the standard model today. He submitted it to the journal Nature. Nature rejected it, as containing speculations too remote from reality to be of interest to the reader. Fermi, stung, published elsewhere and went back to experiments. The phantom, meanwhile, lived up to its billing. A neutrino can pass through a wall of lead a light year thick with even odds of touching nothing. Detecting one was not hard. It was, by every reasonable estimate of the 1930s, hopeless. What changed was that humanity built machines that make neutrinos in floods. In the early 1950s, two American physicists, Frederick Reines and Clyde Cowan, went hunting. Their first plan, in the plain style of the atomic age, was to detonate a nuclear bomb and catch the burst. They realized in time that a nuclear reactor, pouring out trillions upon trillions of neutrinos every second, steadily, would do better. At the Savannah River reactor in South Carolina, they set their trap. Tanks of water laced with cadmium, watched by light detectors, tuned to catch a signature no accident could fake. The double flash, precisely spaced in time, of a neutrino striking a proton. Through June of 1956, the signature arrived, again and again, about 3 times an hour, faint, punctual, unmistakable. 26 years after the letter to the radioactive ladies and gentlemen, Reines and Cowan sent Pauli a telegram in Zurich. "We are happy to inform you that we have definitely detected neutrinos. Take a moment with what had just been confirmed, because it concerns you directly, tonight, in your bed." Pauli's phantom is not rare. The sun's fusion core produces neutrinos in such quantities that roughly 65 billion of them pass through every square centimeter of you, every second, through your thumbnail, through your closed eyes, through the mattress and the floor, and the entire earth beneath you, day and night, without the slightest regard for which is which. In the seconds it has taken me to say this, trillions have crossed you, and in your whole life, the odds are that only a small handful will ever touch a single atom of your body. You are, at this moment, standing in the beam of the most penetrating rain in nature, the rain Pauli invented on a Thursday evening to save a bookkeeping rule, the rain that turned out to be real. The missing energy of every beta decay since the beginning of the universe has been streaming through everything, all along, politely balancing books nobody could read. Pauli's reply was 2 sentences long, and the second is the epitaph of the whole affair. Everything comes to him who knows how to wait. He opened, the story goes, the case of champagne. He had 2 more years to live. He died in 1958. At 58, Clyde Cowan died in 1974. Frederick Renis waited on, and the Nobel Committee did not honor the detection until 1995, 39 years after the telegram, when Renis was 77 years old. Institutions, you may have noticed by now, are slow in this story. The physics never was. Today, neutrino observatories watch the sun's core and dying stars through kilometers of ice and rock, and every one of them is downstream of a single act of trust, that when the books refuse to balance and the symmetry says they must, you do not fire the symmetry. You conclude that something real is missing, and you go and find it. The ledger had become a hunting license. And with that, a door swings open that we have not yet walked through. Energy, momentum, angular momentum. Every conserved quantity we have met tonight came from a symmetry of space and time, something you could do with a clock or a compass. But the 20th century was about to discover conservation laws with no clock and no compass behind them. Ledgers kept by symmetries hiding somewhere no one had thought to look, not in the world around the particles, but inside the particles themselves. The most familiar of them guards the charge in every wire of your sleeping house, and its symmetry is a dial that no instrument in the universe can read. Electric charge is conserved. You have known that, in some form, since school. Charge is never created or destroyed, only moved and rearranged. A lightning stroke hurls tens of coulombs from cloud to ground in a millisecond of violence, and when the thunder fades, the total charge of the world is exactly what it was. The rule is enforced with a strictness that beggars description. If charge conservation could fail even slightly, the electron, the lightest particle that carries charge, would have something to decay into, and electrons everywhere would slowly be winking out of existence. Deep beneath the Gran Sasso mountain in Italy, an experiment called Borexino spent years watching for a single such event in an ocean of ultra-pure fluid, and found none. The conclusion, published in 2015, the electron's lifetime, if it decays at all, exceeds 6.6 times 10 to the 28th power years. That is around 5 billion times the current age of the universe. Of all the ledgers in nature's bank, the charge ledger may be the most incorruptible, and by everything this night has taught, you should now be asking the Noether question, by reflex. If charge is conserved, what is the symmetry? What can you do to the world, smoothly and by any amount, that leaves the laws looking the same, and casts electric charge as its shadow? Here is the strange and wonderful answer. It is not anything you can do with a clock, a ruler, or a compass. The symmetry behind electric charge lives inside the mathematics of matter itself. Quantum theory describes an electron by a wave, and that wave carries, at every point, a kind of internal dial, an angle, called its phase. The phase is not the electron's position, or speed, or energy. It is an internal setting, and here is the crucial fact. No experiment in the universe can read the dial's absolute position. What experiments can detect is only how phases compare and interfere. Turn every dial in the universe together, by the same amount, and every prediction of physics comes out identical. It looks the same. That is a continuous symmetry, as smooth as the circles, a family of rotations, not of space, but of an invisible interior angle. Run it through Noether's machinery, and the conserved quantity that emerges is electric charge. The most incorruptible ledger in physics is the shadow of a dial no one can see, on an angle no one can measure, hidden inside every particle of matter in existence. When physicists say, in their compact jargon, that charge conservation comes from an internal symmetry, this is what they mean, and it means the theorem's writ runs beyond space and time entirely. Anywhere lawfulness has a sameness in it, however abstract, however hidden, there is a ledger. The universe's bookkeeping departments are not all housed in the visible world. And then, in the middle of the 20th century, physicists turned the theorem around and made it a factory. The pivot has a history worth telling, because it begins with a failure. Hermann Weyls, in fact, in the very year of Noether's paper. In 1918, Weyl proposed that the scale of length itself might be a local symmetry of nature, that the universe might not care about the size of your measuring rod from place to place, and he called the idea gauge invariance, gauge as in the gauge of a railway track. Einstein admired the mathematics and killed the physics with a single observation, delivered essentially by postcard. If length were locally adjustable, atoms that had travelled different histories would emit different spectral lines, and they visibly do not. Weyls' symmetry was wrong. But a decade later, with quantum mechanics in hand, the idea was reborn in transfigured form, not the scale of length, but the electron's internal phase dial. Suppose, and here is the audacious move, nature does not merely permit turning all the dials together, everywhere at once, but permits turning each dial independently, by a different amount at every point of space, and at every moment of time. Demand that much freedom, and bare quantum mechanics cannot deliver it, unless something new exists in the world to reconcile the differing dial settings from point to point. Work out what that something must be. Its properties are forced, one by one, and you find it must be a field, massless, long-ranged, coupling to charge, obeying precisely Maxwell's equations. It is light, electromagnetism, the entire electric and magnetic world, every photon, every radio wave, the glow of every screen, is what the mathematics conjures when you insist that an invisible internal dial may be set freely at every point of the universe. The old name stuck, fossil of Weyls' beautiful failure, gauge symmetry. Physicists had stopped discovering symmetries in their laws. They had begun deriving laws from their symmetries. If the trick worked once, it should work again with richer dials. And in 1954, two physicists at Brookhaven, Chen-Ning Yang and Robert Mills, built the general machinery, gauge theory for interlocking families of internal dials. The unveiling did not go smoothly. When Yang presented the work at Princeton, Wolfgang Pauli, who, characteristically, had tried the same mathematics himself and abandoned it over one unresolved flaw, began interrupting with a single repeated question: what is the mass of this field? Yang had no answer. The mathematics seemed to demand new massless force carriers, which should have been as obvious in nature as light itself, and were nowhere to be seen. The badgering grew so fierce that Yang stopped and sat down, and Robert Oppenheimer had to intervene. We should let Frank proceed. It took physics a further decade to answer Pauli's question, through the idea of symmetries hidden by their own consequences, a story whose ending, the Higgs mechanism, we have explored on this channel before and will not rerun tonight. What matters for our thread is the outcome. Yang-Mills gauge theory, completed by that repair, became the language of every force in the Standard Model. The strong force that binds atomic nuclei, a gauge symmetry, with its own family of internal dials. The weak force that drives beta decay, Pauli's old haunt, a gauge symmetry. Electromagnetism, the original, the Standard Model of particle physics, the most precisely confirmed theoretical structure in human history, is at bottom a short list of symmetries, and nearly everything else about it follows by Noether logic, the way a cathedral follows from its blueprint. And do not let the abstraction hide the reach of this. The Wi-Fi carrying a signal through your wall right now, the current sleeping in the wires of your house, the chemistry holding your body together, all of it is electromagnetism. And electromagnetism, physics now understands, exists because the universe grants total local freedom to an unreadable dial. Somewhere in your room, A photon is crossing from a router to a phone, and the deepest available explanation of why photons exist at all is a sentence about symmetry. That is not a metaphor, that is the actual content of the theory. But the demonstration that stops the breath is what symmetry did for the particles themselves. By the late 1950s, accelerators were churning out new particles faster than anyone could make sense of them. Dozens upon dozens. A zoo without a keeper. In 1961, Murray Gell-Mann and, independently, Yuval Ne'eman, an Israeli army colonel who did physics between military postings, found the pattern. The particles arranged themselves into families whose shapes were dictated by an abstract symmetry, geometric patterns of 8 and 10. Gell-Mann, with a physicist's sense of humor, called it the eightfold way. And in 1962, at a conference in Geneva, he stood up and pointed at a hole. One of the 10-member family portraits had 9 known faces and 1 vacancy, and the symmetry dictated the missing member's properties in advance. Its charge, its strangeness, and its mass, near 1,680 million electron volts. He named it before it existed, the omega minus. Experimenters at Brookhaven went hunting with a bubble chamber, photographing particle tracks by the tens of thousands, frame after frame after frame. In February of 1964, after roughly 100,000 photographs, there it was, one track, kinking through the frame, decaying exactly as prescribed, with a measured mass of 1,672 million electron volts. The vacancy was filled. Symmetry had predicted a particle of matter, its existence, its properties, its mass, to within 0.5%, before any human being had ever seen one. The pattern in the families pointed, a few years later, to something deeper still. The particles in those portraits are themselves built of smaller constituents, the quarks, and the eightfold patterns are the shadows those constituents cast. An org chart drawn by symmetry had led physics, hand over hand, to a new bottom layer of matter. Stand back and look at the century then, the way this night has taught you to look. 1918. Symmetry explains the ledger's physics already had. 1930. Trust in a ledger predicts the neutrino. 1954 onward. Demanded symmetries generate the forces themselves. 1962. A gap in a symmetric pattern names a particle, its properties, and its mass, sight unseen. This is what physicists mean when they call symmetry the deepest organizing principle in science. Not that it is pretty, but that it produces. It found the quarks. It built the standard model. It is, quite literally, how humanity read the parts list of the universe. And yet the century had one more lesson to teach about symmetry, and it is the strangest one of all, because it began on the day a symmetry that everyone knew had to be perfect, a symmetry so obvious it was barely worth stating, was put to the test in a freezing laboratory in Washington, and failed. Cast your mind back to the snowflake. Early tonight we sorted symmetries into 2 kinds, the smooth kind, like a circle's rotations, which come in all sizes, down to the infinitesimal, and the click kind, like the snowflake's 60-degree jumps, or a mirror's flip, which happen entirely, or not at all. Noether's theorem, we said, speaks only of the smooth kind, but the click symmetries had their own quiet standing in physics, and none seemed more secure than the mirror. Surely, the laws of nature do not distinguish left from right. A film of any physical process, viewed in a mirror, should show a process that is equally lawful. Your heart is on the left, but that is an accident of biology's history, not a decree of physics. Molecules come in left and right-handed versions, but both are equally allowed. By the 1950s, this mirror symmetry, which physicists call parity, had been checked with precision in the electromagnetic force and the strong nuclear force, and it held perfectly. It was so obviously universal that checking it elsewhere seemed like checking whether arithmetic works on Sundays. Then came a puzzle from the particle zoo. Two strange particles, called at the time tau and theta, appeared to be identical in every measurable respect. Same mass, same lifetime, same charge. Yet they decayed in ways that, if parity held, no single particle could combine. Two particles alike in everything, differing only in their mirror manners. It was too tidy and too weird. In the spring of 1956, two young theorists, Sung-Dao Lee of Columbia and Chen-Ning Yang, the same Yang of the gauge theory, sat down with the literature and asked a question of beautiful impudence. What is the actual evidence that the weak interaction, the force behind beta decay, our old friend from the Pauli chapter, respects the mirror? They combed the record and found, to general astonishment, that there was none. Parity in the weak force had never been tested, not once. Physics certainty was pure habit. Lee and Yang published a short paper pointing out the gap and proposing experiments that could close it, and most of the profession shrugged. The expectation of symmetry ran that strong. Pauli himself, Pauli, of all people, the man who had once bet on an invisible particle rather than doubt a symmetry, wrote to a colleague that he did not believe the Lord was a weak left-hander, and that he was ready to stake a very high sum that the experiments would come out symmetric. The person who actually did the experiment was Chien-Shiung Wu of Columbia, and she deserves to be known in every household that has ever benefited from a fact. Born near Shanghai in 1912, encouraged by a father who founded a school for girls in an era when China educated almost none, she had sailed for America in 1936, worked on the Manhattan Project's uranium enrichment during the war, and built a reputation as the physicist you went to when a beta decay measurement absolutely had to be right. Colleagues called her, with a mixture of affection and precision, the First Lady of Physics. Wu was among the finest experimental physicists of the century, a virtuoso of exactly the technique the test required. Beta decay, her lifelong specialty. Through the freezing December of 1956, at the National Bureau of Standards in Washington, she and her collaborators cooled a sample of radioactive cobalt-60 to within 1/100th of a degree of absolute zero, cold enough to line the atomic nuclei up in a magnetic field like tiny compasses, all spinning the same way, and then simply watched which way the beta decay electrons flew out. If the mirror symmetry held, the electrons would show no preference between the two poles of the spin. The mirror image experiment would look the same, so up and down would be indistinguishable. They were not indistinguishable. The electrons poured out preferentially opposite to the direction of the nuclear spin, a lopsidedness so large there was no arguing with it. The mirror image of a weak interaction process is not, in general, a process our universe performs. In January 1957, the result went public, and the shock ran through physics like current. Pauli, informed by letter, was flabbergasted, and observed with rueful gratitude that he had never gotten around to placing the actual bet. He could afford, he said, the loss of his reputation, but not of his capital. Within 10 months, the fastest turnaround in the prize's history, Lee and Yang received the Nobel Prize. Chien-Shiung Wu, whose hands and judgment had wrung the answer from nature, was passed over, then and every year after, an omission physicists have argued about ever since, and one that will sound, by now, like a familiar chord in this story. The universe, it turned out, is not ambidextrous. In its weak dealings, it is left-handed. The neutrinos Pauli invented all spin, so far as any experiment has ever seen, with a single-handedness, like screws, threaded only one way. Nobody knows why. 70 years on, the handedness of the weak force remains a brute fact at the bottom of the standard model, a signpost pointing at physics still undiscovered. The mirror's fall taught physics to hold even deeper certainties up to the light, and the certainties kept partially failing, in instructive ways. Combine the mirror flip with a second flip, swapping every particle for its antiparticle, and you get a compound symmetry called CP, which survived Wu's earthquake and was declared the true, restored balance of nature. In 1964, it too was caught cheating, subtly, in the decays of particles called kaons, a discovery so consequential that it may be connected to why the universe contains matter at all, rather than annihilating into pure light at birth. A mystery we have circled on this channel before, and one that is very much still open. And yet the retreat stops, decisively, at the last line. Flip the mirror, swap matter for antimatter, and reverse the direction of time, all three together, a compound operation called CPT, and quantum field theory stakes its very consistency on the claim that this combined symmetry is exact. Here, the experiments are a fortress. The charge-to-mass ratio of the proton and the antiproton have been compared and found identical to 16 parts in a trillion. Particle and antiparticle masses in the kaon system agree to roughly 1 part in 10 to the 18th. The cliques can fail, nature seems to say, but not all of them at once. And even the smooth symmetries, Noether's own, turned out to have 2 remarkable fine print clauses. The first, a law can be perfectly symmetric while its outcomes are not. Balance a pencil on its tip, the situation is flawlessly rotationally symmetric, no direction is preferred, and yet the pencil must fall, and it must fall some particular way. The symmetric condition is unstable, so the world ends up lopsided, while the law stays even-handed. Physicists call this spontaneous symmetry breaking, and it is the answer, incidentally, to Pauli's brutal question about the mass of the Yang-Mills field, the mechanism by which hidden symmetry gives particles their mass, a story told in full on one of our earlier nights together, and left in peace now. The second clause is stranger. A few symmetries that hold perfectly in a classical theory are broken by the act of quantization itself. Physicists call these failures anomalies, and far from being embarrassments, they are precision tools. The rate at which a neutral pion decays into 2 photons, measured, large, and at first theoretically baffling, is correctly predicted only when the anomaly is included, one of quantum field theory's quiet triumphs. Symmetries, in other words, are not a wallpaper of universal perfection. They are structure, some exact, some broken by instability, some broken by quantum mechanics. One, the weak mirror, broken for reasons nobody has yet found. Each fracture line, mapped precisely, has been a doorway. Physics' modern frontier runs on exactly this method. Searches for proton decay, none seen, lifetime beyond 10 to the 34th years. Probe whether the ledger guarding matter itself is exact or merely very good. Laboratory time crystals probe how time's own symmetry can spontaneously fold. And theorists of quantum gravity conjecture that at the deepest level, no ledger not backed by a gauge symmetry survives at all. The theorem drew the map. The breaks mark the treasure. Which brings us, at last, back to the person who drew it. We left Emmy Noether in the 1920s, unpaid and unstoppable, rebuilding algebra, while physics slowly awoke to what she had handed it. Her greatest years were ahead of her, and so was the catastrophe, because in January of 1933, in the country that had refused her a title for being a woman, a government came to power that would now refuse her existence for being a Jew. The symmetry of her story is about to turn cruel, and it is time to see how the woman who explained what survives all transformations faced the transformation that was meant to erase her. The 1920s were, by every account, her great decade. Officially, almost nothing changed. The habilitation finally came in 1919, under the New Republic, then a professor's title of the emptiest kind, extraordinary and unofficial, carrying no chair, no duties, and no salary, plus, eventually, a small teaching stipend for algebra. Unofficially, Emmy Noether became one of the most influential mathematicians on Earth. In 1921, she published a paper on ideal theory that did for algebra something like what her theorem had done for physics. It found the hidden architecture under a century of scattered results. Mathematicians today speak of Noetherian rings, Noetherian modules, Noetherian conditions. Her name lowercased into the permanent vocabulary of the subject. The quiet immortality mathematics reserves for its very few. Students came to her from everywhere. The Noether boys, they were called. Young men from the Netherlands, Russia, Japan, Israel to be, and she taught them in a style nobody forgot. Loud, fast, joyful, utterly indifferent to appearances, thinking aloud at the blackboard and giving her ideas away with both hands. Her lecture courses, written up by one such student, became the seed of the textbook that taught modern algebra to the world. Her generosity with ideas was itself a legend. She published results under students' names, seeded whole careers with suggestions tossed off at the blackboard, and treated priority, the currency most scientists guard most jealously, as if it were beneath her notice. The Russian topologist Pavel Alexandrov, who knew her well and spent long walks with her when she taught a guest semester through a Moscow winter in the late 1920s, called her flatly the greatest woman mathematician of all time, and remembered that what she radiated was not intimidation, but warmth. Mathematics, in her orbit, felt less like a competition than like a common inheritance being handed out. In September of 1932, she stood before the International Congress of Mathematicians in Zurich and delivered a plenary address, the first woman in the Congress's history so honored, before an audience of roughly 800. It had taken until her 50th year, but the recognition was real, and it was hers. It lasted 4 months. On January 30th, 1933, the National Socialists took power in Germany, and in April the new government issued its law for the restoration of the professional civil service, the bureaucratic instrument by which Jewish scholars, and those deemed politically unreliable, were to be purged from German universities. Göttingen's Mathematics Institute, the wonder of the scientific world, was gutted within a single year. Emmy Noether was among the very first 6 faculty members whose right to teach was withdrawn. She qualified for the regime's hatred 3 times over, as a Jew, as a woman, and as a known pacifist of the political left. The notice arrived by official letter. She was 51 years old. She had held her hard-won teaching permission for 14 years, and her country took it back with a form. What she did next is the part of the story that people who knew her could never tell without wonder. She kept teaching. The university buildings were closed to her, so the seminar moved to her apartment, and the mathematics continued without so much as a dropped week. It is a summer afternoon in 1933, in a modest flat on a quiet Göttingen street. The furniture has been pushed back. A portable blackboard leans against the wall, already half covered in her rapid, impatient chalk. A handful of students sit where the chairs allow. There is a knock, and one more student comes in late, and the room goes still for a beat, because he is wearing the brown shirt of the Nazi SA, the stormtroopers, the uniform of the movement that has just ended their teacher's career. Every eye goes to Emmy Noether. She looks at the young man, and she laughs, actually laughs, waves him to a seat, and turns back to the board, mid-theorem, as if the uniform were a wet umbrella he had forgotten to leave at the door. The seminar resumes. The algebra, which does not know what year it is, goes on. Witnesses to those months describe her without a trace of performed courage. No bitterness, no speeches, her attention simply elsewhere, on the structures, on the students, on the work. Hermann Weyl, who was there, and who spent that year fighting to save her, fixed it in a sentence. Her courage, her frankness, her unconcern about her own fate, her conciliatory spirit were, in the midst of all the hatred and meanness, despair and sorrow surrounding us, a moral solace. Weyl said something else that year, and it costs a man like Weyl something to say it. He was ashamed, he admitted, to occupy a privileged position beside a colleague he knew to be his superior as a mathematician in many respects. The scramble to save the purged scholars of Germany was by then underway across the Atlantic. Run through an emergency committee, that matched refugee academics with American colleges, funded in part by the Rockefeller Foundation. The great research universities snapped up the famous men. For the greatest woman in mathematics, the offer that materialized was modest, almost to the point of insult, and generous, almost to the point of tears, both at once. A one-year visiting professorship at a small women's college in Pennsylvania called Bryn Mawr. She took it. In the autumn of 1933, Emmy Noether left Germany forever. And here the story, so full of doors closed in her face, opens one last unexpected door and puts light behind it. By the accounts of those who knew her, the 18 months that followed were among the happiest of her life. At Bryn Mawr, for the first time anywhere, she was simply a professor, titled, salaried, wanted. She taught a small circle of young women, in her chaotic polyglot English, with the same overflowing generosity that had raised the Noether boys. Once a week she took the train to Princeton to lecture at the Institute for Advanced Study, where Einstein and Weil had landed, an institution she needled, with a grin that survives in the anecdote, as the men's university, where nothing female is admitted. She was 52, in a new country, in a new language, beginning again. Colleagues talked of arranging something permanent, something finally equal to her. In April of 1935, doctors found a large tumor, and she underwent surgery to remove an ovarian cyst. For 3 days she seemed to be recovering well. On the fourth day, April 14th, 1935, she collapsed suddenly, and within hours she was gone. She was 53 years old. The mathematical world learned the news in stunned disbelief. She had told almost no one she was even ill. On May 4th, the New York Times published a letter signed by Albert Einstein. In the judgment of the most competent living mathematicians, he wrote, "Fräulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began." He wrote of her years teaching for nothing, of the exile, of the students she carried with her to the end. Weil, delivering her memorial address at Bryn Mawr that spring, reached past mathematics entirely. She did not believe in evil, he said. Indeed, it never occurred to her that evil could play a role among men. Her ashes were buried beneath the walkway of a cloister on the Bryn Mawr campus, under a small marker that gives no title, no theorem, no epitaph, only the letters EN and the 2 years, 1882 and 1935. Students walk over it daily, mostly unknowing, on their way to class. In Göttingen, meanwhile, the institute she had illuminated was a shell. When the regime's education minister asked Hilbert, at a banquet, how mathematics stood in Göttingen now that it was free of the Jewish influence, the old man is said to have answered, "Mathematics in Göttingen, there is really none any more." The government that drove her out believed it was purifying something permanent and disposing of something disposable. It had it exactly backwards, and the proof is in this sentence. The Third Reich lasted 12 years, and tonight, 90 years after a quiet funeral in Pennsylvania, the physics of every wire, skater, star, and second of your day still runs on the theorem of Emmy Noether. Theories are mortal. Regimes are astonishingly mortal. A theorem is forever, and so, it turns out, is a certain kind of person, the kind whose central quantity nothing in the world could make change. She never knew what her theorem would become. She could not have. The gauge century, the eightfold way, the neutrino's vindication, the standard model, all of it lay on the far side of her early death, which leaves us, on our last stretch of the night, with the promise this whole journey was named for. We have the theorem now. We have watched it explain the ledgers, survive the revolutions, predict the particles, and outlive its maker. It is time to collect everything into one final look at the world, and to say, plainly and at last, why once you have learned it, you cannot see things the same way again. We began tonight with a promise, and the hour has come to keep it, plainly, with everything now on the table. Here is what changes. once and for all, when Noether's theorem takes up residence in your head. Before the theorem, the laws of nature look like a rulebook. That is how every one of us was taught them, a list of decrees, handed down from nowhere. Energy shall be conserved. Momentum shall be conserved. Angular momentum shall be conserved. Learn the rules, apply the rules, pass the exam. And if you ever asked why those rules and not others, why the universe should keep ledgers at all, the honest answer, for 200 years of magnificent science, was silence. The rules were facts without parents. Physics could use them, it could not introduce them. After the theorem, the rulebook dissolves, and what stands revealed behind it is not a longer list of rules, but a shape. The universe, as far as any instrument has ever probed, is the same from one moment to the next, the same from one place to the next, the same in every direction, the same at every steady glide. And that sameness is not a backdrop to the laws, it is the laws. Each conservation rule you memorized in school is one aspect of the sameness, translated into bookkeeping. Energy is what time's indifference looks like from inside. Momentum is space's indifference. Angular momentum is directions. The commandments were never commandments. They are shadows, cast into the world of things by the symmetry of the stage the things stand on. Physics does not have a rulebook. It has a geometry, and the geometry writes the rules. The physicist Eugene Wigner, whose Nobel citation named the symmetry principles themselves, put the hierarchy in one sentence. Symmetries stand to the laws of nature, as the laws of nature stand to events. Events obey laws. Laws obey symmetries. In the century since a July session in Göttingen, physics has climbed one full story up the structure of reality, and found the floor above the laws already furnished, waiting, with a woman's theorem for a staircase. And here is the quieter half of the promise, the part that concerns not physics but you. The reason science works at all, the reason an experiment done once teaches you anything about the world's behavior tomorrow, is that the laws do not drift with the calendar. Repeatability is time translation symmetry, worn as a method. But time translation symmetry, Noether showed, is energy conservation. Read that twice, slowly, because it may be the single most elegant consequence of everything we have traced tonight. The conservation of energy and the possibility of knowledge are the same property of the universe, encountered from two different directions. Every time in your life that you have trusted an old lesson, that fire burns, that dropped things fall, that the sun will rise, you have been banking on the exact symmetry that keeps the stars burning at a steady rate and your heart's chemistry solvent from one beat to the next. A universe that could break energy conservation would be a universe in which experience taught nothing, memory purchased nothing, and no creature could ever learn its way from one day into the next. We do not merely live under the theorem's ledgers. We are the kind of thing that can exist only because the books balance. So take the theorem for one last slow walk through your closed-eyed evening and watch the world change under it. Somewhere a night skater pulls her arms in and blurs, and what you now see is not a trick of athletic grace, but the isotropy of space itself, collecting its due through a human body. Overhead, past your ceiling and your weather, the Earth is banking around the Sun, on Kepler's silent schedule, sweeping its equal areas, the same shadow of the same symmetry. At planetary scale, 4 centuries after a court astronomer first noticed the books balancing, and had no idea he was reading geometry. In the wall beside you, a current dreams along a copper wire, guarded by a ledger kept on an angle no instrument in the universe can read. Your coffee cooled tonight by exactly the warmth your kitchen gained. Your body is spending sunlight that was minted in the sun's core before your ancestors had names. And through it all, through you, 65 billion neutrinos a second are falling like weightless rain, the missing column of a ledger, made flesh. Because one man in Zurich trusted the symmetry more than he trusted the visible world. Nothing in your world has changed since last night, and nothing about it can look the same. Every ordinary steadiness around you, every object that persists, every rule that holds, every process that repeats, is the visible face of an invisible sameness, the shape of the stage showing through the play. Honesty asks one more thing of us before we rest, and it is the thread we will leave gently open, in the dark, for another night. The theorem explains the ledgers by the symmetries. It does not, and cannot, explain the symmetries. Why is the universe the same from moment to moment and place to place? Why this stage, with this shape, rather than any other, or none? Physics has climbed one story and found the next landing dim. We keep checking the floorboards, of course. Starlight that left its galaxies billions of years ago arrives still speaking our laboratory's atomic language, and every such photon is a report from the distant past confirming that the sameness has held across most of cosmic history. But confirmation is not explanation, and no measurement of a symmetry can ever tell you why the symmetry is there. Perhaps the symmetries are bedrock, the final, parentless facts. Perhaps they too are shadows of something deeper, not yet named, waiting for its own Emmy Noether in some century ahead, someone sitting, even now, in whatever room our age keeps its doors closed against. The universe does not keep its rules in a rulebook, it keeps them in its shape. What keeps the shape, nobody knows. It looks the same, we say, turning the world in our hands like the circle it resembles, and the whole harvest of modern physics is folded into those 4 small words, along with everything they have not yet told us. Before we close the book, look back once along the whole road, because a pattern is lying there that we never planned and could not have invented. The story of conservation, told honestly, is carried at its 3 hinges by 3 women, each working in a century that had no place for her. In the 1700s, Émilie du Châtelet, barred from the academies of France, assembled the argument and the evidence that gave energy its birth certificate. That put the living force on the books in the first place. In 1918, Emmy Noether, barred from the faculty of Göttingen, explained the books, proved that every ledger is a symmetry seen from the inside, and drew the map of where the ledgers run out. And in the winter of 1956, Chien-Shiung Wu, who would be passed over by the prize committees for it, put the oldest and most obvious symmetry of all to its first real test, and watched it fail, teaching physics that the shape of the stage must be measured, never assumed. Origin, explanation, and correction. The 3 ages of humanity's deepest law, each one advanced from outside the locked rooms of its era. Perhaps that is coincidence, or perhaps there is a plainer reading, that the people a system refuses to admit are under no illusion that the rules of the room are the laws of the universe. And it is exactly that distinction, between the arrangements we make and the symmetries that hold regardless, that this whole night has been about. The rules of the room change. What she found does not. She asked for so little, in the end, a blackboard, some students, a problem worth the evening, and she left the deepest sentence anyone has yet read from the book of nature. What cannot be changed is what the changeless parts of reality are telling you. Once you learn about this theorem, you can't see the world the same way, and tonight, perhaps, as the ordinary constancies of your room keep their perfect books around you, you will not want to. Thank you for spending this night with Emmy Noether's theorem, and for walking all the way down to the floor beneath the laws of physics. If this kind of exploration is how you like to end your day, a like or a subscribe would mean a great deal. It is a small thing for you, and it genuinely helps me keep making these long, slow journeys. And remember, the next time you watch a skater spin, or feel a doorway hold its shape, you are watching the sameness of the universe, quietly balancing its books. Good night, and may you never look at the ordinary world the same way again.